I mean, the schedule says we start with vector spaces from lecture 1. We will, but before that, let me just give a broad context as to what is this course about and why is it useful to take it. If you were to ask me to tell you in one sentence what is the course about, I'd say the course is essentially about high dimensional thinking. Okay, what that means is thinking about objects that have many degrees of freedom. Okay, why is that important? Because we live in a as far as we know, three-dimensional world. So 3 dimensions should be enough. No, we don't have to think about 10-dimensional space to make a living. But it turns out, even though we live in a 3-dimensional world, and most of the things appear to be just 3-dimensional, unfortunately, information is not. And most of the things in the world are high-dimensional. That means there are many things that we would have to take into account when dealing with the world. So I've listed some of the points here. For example, a lot of things that we come across in science and engineering and medicine are multidimensional. There are lots of different factors that are associated with the phenomenon that we are interested in. This is for the engineers. So in undergraduate engineering, how many of you have had that course in linear algebra or matrix theory in your undergrad? You've had, okay. You've had. Did you have? You did, okay. I did not. We had a short chapter on basic matrix theory, and that's it. We did not have a full-blown course on linear algebra, right? And most of the things that taught in the engineering undergraduate course is usually focused on relatively simple systems that are unidimensional. And for unidimensional systems, and the kind of systems that we deal with most of engineering, electrical, mechanical, or civil, or chemical for that matter, calculus is good enough. If you're comfortable with calculus, you can get through undergraduate engineering without any problem. And the kinds of systems that we come across in engineering are usually single input, single output, which are usually abbreviated as SISO. These are the only kinds of systems that we deal with. If you've done electrical engineering, if you've done signal systems, signal processing or control theory, you're always dealing with a system that takes one input, x of t, if it's time, and you have one output. Okay, this is, of course, this is how you start with systems theory and understanding systems. But unfortunately, real-world applications don't fit into this. It turns out there are lots of things that go in and lots of things that come out. So we have to eventually, if you want to do real useful stuff, you have to get to multidimensional way of thinking. And many of the analysis tools that is taught in classical engineering, Fourier, Laplace, Z transform, all that is unidimensional. You're always dealing with just one signal. That of course doesn't work. And if you have a mechanical engineering background, from what I know, the dynamics is also only taught for single degree of freedom systems, not something more. But as I said, that's not true. The real world has multiple degrees of freedom. There are many causes and effects for things that we deal with. We don't just measure one thing, we often measure a lot of information. So we need to have a way of dealing with all this this multidimensional data. And so calculus, univariate calculus is not enough. You need something more. The answer is not necessarily multivariate calculus. Also because maybe if you go 100 years back, our best tool for maybe solving some of these problems was calculus. But now we don't solve problems analytically. Most of the problems get solved by a computer, right? So you need to know tools that are appropriate for you to use so that you can formulate the problem so that a computer can solve it. Okay. For that, again, is so to deal with that is essentially the role of linear algebra, and that's what we'll cover the first part of the course. Right. So the world is multidimensional, and the world is also uncertain. Right. So this is again obvious. I don't have to go through this. There is noise and uncertainty in every measurement that we make. Actions that you take don't always result in the effect you expect because there are other factors that are acting on the system. So you expect something and it does not happen. So there is uncertainty there as well. But even though there is uncertainty, I mean, we could say, okay, this is random and I cannot do anything about it. If it is like that, then of course, then you cannot do anything about it. But it turns out that random is not truly random. There is some structure to it. Okay, this is what people have observed, and it's this structure that we can exploit to do better than saying, we can't do anything about it because it's random and I cannot tell you what will happen next. But with most systems that have uncertainty associated with them, even though you might, for example, coin toss, even though you cannot say what the next outcome is going to be, over a long set of trials, you can actually make a good guess. Okay, so it's that structure that I'm talking about, and that's what we try and exploit to do the best we can with the uncertainty that we have to deal with. Right, and basically we need additional tools. Yeah, please. Yeah, we need additional tools beyond the tools that we've learned maybe in undergraduate engineering for dealing with deterministic systems. So that's essentially probability theory and statistics that helps us to deal with this. Right, and the last one, or the third main reason is whenever we are trying to solve a problem, there are often many options available to us. Okay, and many of these options might actually be, it might not be clear which option to choose. Okay, for example, you might have a system where there are lots of different buttons you can push to get the same output. Then the question would be, which set of buttons do I choose? There might be a lot of different knobs that I can turn to get the same output. And the question is, which option do I choose? Okay. Well, you could say choose any one of them, but then you could ask, okay, is there a set of exact positions that I can place the knobs in so that that particular set of positions is some way desirable. Okay, so you have situations like that. You might be making a lot of measurements, and if the number of measurements you're making is not big enough for you to solve a problem, then there are, let's say I have a system to make it more concrete. Okay, you're making a bunch of measurements. Okay, x1, x2, so on and so forth. Okay, and often it turns out that the system that you're dealing with is so complex or so high dimensional that we might not be able to get as many measurements as we want. Okay, which means, and your goal is to use these measurements to estimate or know something about the system. Okay, because we are not taking enough measurements as required to exactly say something meaningful about the system, there are many different possible states for the system that could have given me the same output. Okay, so when you deal with stuff like this, then that means I have a set of measurements. This could give me an infinite number of possible systems. I have an infinite number of possible systems that could have produced this. Now, how do you solve something like this? So, and this is where something like optimization comes in, where you say, okay, there are infinite number of possibilities, but there are some structures in the possible system that I have, which I think is more reasonable than others, and you formulate your problem in such a way so you formulate the problem by incorporating some structure to the outcome that you're looking at, and then you try and find out or try and estimate the system that gives you the best possible structure that you're interested in. Okay, I'm being very hand wavy here. We will get into some of the specific details as we get later into the course. So you can have situations like that. And then in engineering design, of course, if let's say you have to design a robot, there are lots of different parameters you have to decide. Now, how do you choose the best parameters for the robot? So then you go about saying, okay, I define this as some criteria that I set, and the design parameters that I choose should satisfy that criteria. Right. So the problem then would be, because you have so many options, is to search through this set of, or this option space of different options that you have, and then choose what you define as the best one. Okay, that's essentially what optimization is about. And again, there are tools for formulating such problems mathematically and solving them very efficiently. Okay. So these are three aspects, and the three of them are covered by these three topics that we will talk about: linear algebra, probability theory, and optimization. Okay. I'll briefly talk about what these are, and then we'll quickly move on. So linear algebra. So algebra is essentially the study of variables and how you arithmetically manipulate them. If people are interested, it comes from this Arabic word called algebra. It turns out that also means bone setting, which basically means reunion of broken parts. And linear algebra is algebra that deals with systems that are linear. Okay, essentially, system of equations like this, set of linear equations, and studying such set of linear equations is at the core of linear algebra. A more modern version or definition of linear algebra would be study of vector spaces and linear maps. That again, we'll see what vector spaces are and what linear maps are as we go on. And you could ask, okay, why would somebody be interested in a set of equations like this? It turns out, I mean, mathematically, these are fun things to study. People do things in mathematics just because it's fun to do. They're not. Most of them are not interested in whether it's applicable to real life. So these are fun things to do. And it also turns out that many problems in the real world can actually be formulated like this. These are actually very useful in practice. And the different terms that you see here, the x's that you see could be inputs or parameters of the problem that you're interested in. The y's on the right hand side are outputs or measurements that you make. And these coefficients a, I, j tell you something about the physics of the problem, how the input and output are related. Okay. And linear algebra essentially deals with understanding and understanding, manipulating, and efficiently solving problems of this form. Okay, that's a very brief introduction about what linear algebra is. Probability theory, again a branch of mathematics that deals with probability, which is a measure of how uncertain an event is. Provides tools for representing, analyzing, and manipulating probability of events. Some of the topics that we will talk about are what are probability distributions, densities, random variables, expectation, variance, covariance, and things like that. And more importantly, things like Bayes' rule. And we won't talk about any specific probability distribution except for the Gaussian or the normal distribution, which is arguably the most important distribution in statistics. It's that. And then optimization, as I said before, is essentially a mathematical field where you're looking at the selection of a best possible element from a set of alternatives that you can choose from. I mean, that's again a very broad definition. There are of course different types of optimization problems that we can come across. What we will talk about in the course will be what are called continuous optimization problems. That's essentially we're searching for solutions involving a bunch of real numbers. Okay, again, what that symbol means, we'll cover that later. Okay, and mathematically, what an optimization problem would look something like this. So as I said before, you have a set of alternatives. Let's say this is the space of alternatives that I have to choose from, and let's assume there are an infinite number of them. And the way you choose them is by saying, okay, each of these alternatives has something good or bad associated with them. Okay, and you capture the essence of how good a particular point is through a function called f of x. Okay, so this function tells me if I put in a point from this space that I'm searching over, this tells me how good that point is. Okay, and what you're trying to do, I've said minimum. Okay, let's say this function tells me how bad that point is. Okay, and what you would like to do is to minimize this. I would like to choose a solution x such that this is minimized. That's the point with the least badness. Okay, that is one form of optimization problem. Your goal is to find an x, which we will call x star. Okay, such that this badness is kept as low as possible. Okay. This is one form of optimization problem. Usually something like this would be called an unconstrained optimization problem. Okay, because you're free to choose any x. Okay, but there might be cases where you say, no, I cannot choose any x. My x's have to be positive. right? I want the best solution for something like this, but my x has to be greater than or equal to 0. And if you place constraints like this, then it's called constrained optimization, and that's what these gi of x are. These are constraints that you place on your x, which x's have to satisfy. That means you don't have this entire space. You've broken this space up into a region where you can search over, and your search now essentially happens here. This is area that you're not allowed to search over because they don't satisfy the constraint. Okay. Yeah. So that's essentially what mathematical optimization is about, and the field has lots of different ways of looking at this problem, understanding them, and various algorithms for solving stuff like that. Okay. I mean, the reason it must also be clear that I've said continuous optimization, which probably also means there are non-continuous optimization problems. Some of them could be you're not searching over a space of real numbers, but you're searching over the space of integers. Okay, because your problem might you might have a problem where you are searching over different possible alternatives, and those alternatives only take integer values. So you could have things like that as well. Those are a lot more hard to solve. But so because this is an introductory course, we'll only look at continuous optimization problem. So those are 3 areas that we look at. And where are these applied? I've said, I mean, I started by saying these 3 topics are actually applicable in a wide variety of areas, and I list some of them here. Signal processing, control theory, medicine, economics, and so on and so forth. There are lots of other things. Okay. We'll look at a few examples. So, for example, if you talk about signal processing, right? Signal processing deals with, signals that carry some information and how to process and extract information from them. Right? And often in signal processing, we are looking at signals that are functions of time. For example, if you're measuring ECG or EEG, we are all used to seeing stuff like this. Dealing with ECG. This is one form of representing your signal, right? This is essentially the voltage measured by a particular electrode as a function of time. Let's say we call it V of t. And what a trained clinician would do is look at this, and then they try and infer various conditions associated with the cardiovascular system based on the ECG. Okay? So this way of representing the signal is one way of representing it. So you could ask, okay, is there another way of representing this, right? Instead of just looking at the change in the voltage as a function of time, you could ask, maybe there are other ways of looking at things, right? And signal processing deals with this problem of can we look at it in other ways, right? And you could ask, what are those other ways, right? One example would be, imagine a sinusoidal signal, right? So that's the time plot of a sinusoidal signal. So that's one way to represent that signal, right? Another way could be, I don't have to give you the entire time record of the signal. If I give you 3 pieces of information, that's enough for you to know exactly what I'm talking about. Essentially, the frequency of the sinusoid, the amplitude of the sinusoid, and the initial phase, right? So if I had a signal like that, and if I gave you the amplitude, the frequency, and the initial phase, you can exactly reconstruct the full sinusoid using just these 3 parameters. Okay? So an equally good representation of that signal that I have is just these 3 numbers. Okay? So for example, one of a particular way of looking at a signal that we often come across in signal processing is called the Fourier transform, which essentially takes a time domain signal and then asks the question of what all frequencies are there in the signal. Okay. For example, now if you take that sinusoid and take the Fourier transform, it will give you another representation for the signal, not as a function of time, but a function of frequency. Okay, and if you imagine the x-axis as the different frequency components that are present in that signal, you see that it's 0 for all frequencies except for the 1.5 hertz. Okay, which is essentially another way of representing the exact same signal. Okay, so what the Fourier transform offers you is another perspective of looking at a time domain signal. Now, it's a single sinusoid, so you have a peak here. But if you had something that was a sum of multiple sinusoids, then you'd see multiple peaks, which I'll show you later. Right? So that's one way. The Fourier transform is one way of looking at a signal. Right? It turns out that this Fourier transform is simply an example of a very general way of looking at signals, which is essentially this. Okay, any time domain signal x of t can be represented as a sum of some time functions phi 1, phi 2, phi n, all scaled by some number c1, c2, cn. Okay, it turns out the Fourier transform is simply a special case of that particular representation, and signal processing for a majority of signal processing essentially deals with representing signals like that. Now, you could ask, what are these phi i's and what are these c's? Phi i's are, in the Fourier transform case, they would be sinusoids. And what you're doing in the Fourier transform, you're saying, I'm representing any time domain signal as a sum of sinusoids. Okay? You could choose these to be other types of functions, then you'd have a different representation for the same signal. Now, what phi I you choose might depend on the application that you're dealing with. If you're interested in the frequency content, you'll use the Fourier signals for phi I. If you're interested in maybe let's say looking at time frequency characterization of a signal, then this could be some wavelets that you use for phi I, and so on and so forth. Now, you should probably already see the connection between something like this and linear algebra. In linear algebra, we had terms like this: a11 x1, a12 x2, plus a1n xn equals y1. Okay, that looks awfully similar to this. Okay, and there is a connection. You're simply saying x is a linear combination of some phi i's. Okay, and we'll again come to this later. These phi i's are often called basis functions, and another way to think about this is, if I have x of t and I can successfully represent x of t like this, then all I have to tell you are the numbers ci. Okay. If I give you these numbers, then you can perfectly reconstruct x of t. Okay. Very similar to something like this. Okay. And computing the ci's and manipulating them will help you change the signal in the ways that you want for you to be able to extract useful information. Okay. See, for example, let's say we have a time domain measurement like that. Okay. I mean, this is again a made up simple example. I've simply generated a time domain signal that's a sum of different frequency components. Okay. If you take the Fourier transform, it already tells you what Fourier frequency components there are. So there is something very close to 0, which are large with a large amplitude, and then a few other frequency component, and then there is a relatively large frequency component at 3.5. Right? Now, let's say your interest that fast variations that you see, let's say that is, for your application, let's say that is noise. Now, the question would be, how do we get rid of that? Okay. Maybe if you just look at that signal, it's not immediately clear. But if you look at this, maybe it's fairly clear. Let's say this is C1, C2, and C4. And your x of t was originally is represented like this: C1 phi 1 of t, plus C2 phi 2 of t, C3 phi 3. I'll drop the t. Okay. Now, if I want to remove the high frequency component, how would you remove it here? All you'd have to do is make C4 0 and then reconstruct just this. Then you'd find that the fast varying component disappears. Okay. Again, if it's not clear, don't worry, it will become clear hopefully. So, being able to look at a signal from a different perspective makes some of these things easier to deal with. Okay, that's the point I'm trying to get across. I'll skip this. So, I've said this before. If you take the Fourier representation, you get a nice clean representation like this. But then you could ask, is the Fourier the only? What is so special about the Fourier? Turns out there is not. I mean, there is something special, but there is also nothing special about it. There are other ways you can look at the signal as well. Okay. And another very important point is, okay, this way of looking at the signal is one, again, as I said before, one way of looking at it. It turns out that if we think of time domain signals as entities that live in a high dimensional space, that provides a lot of insight that might not be immediately clear with with a pure time domain representation like this. Again, we'll come back to what that means later on in the course. Okay, and one theme that will often come across, at least in the first half of the course, is once you are able to think of things as entities residing in a high dimensional space, with linear algebra, a lot of geometry can be applied for dealing with algebra. So the algebra that you might see, which might look very dense, actually has a very beautiful geometric meaning, which most of us can easily grasp. And it turns out that you can imagine purely in terms of geometry as to how you want to manipulate things, and then there is a corresponding algebraic expression that you can use for implementing it and on a computer and things like that. Okay? And so we'll look at some of those things in as part of at least the first part of the course. I mean, I'll go through some of these fairly quickly. I don't want to spend too much time on this. Again, that was a signal processing problem. For example, if you're looking at control theory, one popular example is a spacecraft. You're trying to control the spacecraft in space. You need to be able to control the position of the spacecraft, 3 variables, and the orientation of the spacecraft. Right? So you're essentially dealing with a problem of controlling 6 degrees of freedom of an object. And of course, there are lots of sensors in your spacecraft. There are lots of different actuators. Now the question is, I'm making, let's say, 100 different measurements from 100 sensors. How do I use these 100 different measurements that are coming in as at a particular rate? Use them to exactly know what is the orientation and position of my spacecraft. That's one part of the problem. And once you figure out where I am, the next thing would be, how do I now control my thrusters and my reaction wheels to maybe translate the spacecraft or change the orientation of the spacecraft. This again is a multi-dimensional problem, because you're trying to control 6 variables and you have lots of different knobs you can turn to change those 6 variables. And there again, linear algebra plays a huge role, and optimization and probability theory as well. Another area, maybe slightly closer to what the kind of problem that we deal with, is robotics. That's an example of a robot that's used for therapy. This is an example of a surgical robot. Again, it turns out in robotics, often what you're interested in, or the most interesting thing, often happens at the very end of the robot. At least with serial robots like this, right? So with the surgical robot, the thing that you're most interested in happens here, and maybe with the rehab robot, maybe the most interesting thing happens there, right? But you see that there are all these different joints. That means I can control the position and orientation of this end effector by turning a lot of knobs. Okay. The question would be, what is the best way to turn these knobs so that I can do what I want to do. Okay. But it turns out robotics is a highly nonlinear or an area where there is a lot of nonlinearities involved. For example, if you think of a simple 2 degree of freedom link, the description of the position of this point P as a function of the joint angle, it's not linear. Okay, but it turns out, even though the kinematics is not linear, the differential kinematics is linear. Don't worry about what that means. It simply means, even though the relationship between my shoulder elbow and my shoulder angle and my elbow angle to the end point of my hand is not linear, the angular velocity of my shoulder and the angular velocity of my elbow is actually linearly related to the end point velocity of. So some of this is again because this linearity is used for solving problems in robotics. Okay, but even if it's not linear, it turns out that ideas from linear algebra are essential for even representing high-dimensional nonlinear systems. For example, the equation for the dynamics of a serial robot would look something like this, where n, c are actually matrices and g is a vector and things like that. Okay, so it is still useful even for nonlinear systems. You of course have linear algebra plays a huge role. Okay, and then statistics. The data that we deal with is heterogeneous, it's high dimensional and noisy, and the core of what statistics is about is again representing data, evaluating relationships between variables, and building and estimating models. Right? And all three areas that we talked about, probability theory, calculus as well, linear algebra and optimization, of course, have a role to play in statistics. Again, earlier, like I said, you had to be able to solve problems analytically, but again, with these days, you don't have to always resort to an analytical solution. Okay. To give you an example, so this is something I pulled out from a recent paper where physical fitness is important. We all know it's a good indicator of whether or not somebody is going to have chronic diseases later on in life. Right? So there is this study where they were tracking what is called this health-related physical fitness, which actually involves measuring multiple variables which are not easy to measure. So they were asking the question, can we predict somebody's, or can we get a good estimate of somebody's physical fitness from variables that are easy to measure, like age, height, weight, body mass index, and all that. Right? And maybe the bread and butter model of statistics is probably the linear regression model, which is basically, again, this should remind you of the equation that I showed in linear algebra. So it's a linear equation relating the different variables that we can measure, age, height, body weight, BMI, to Y, which is basically the physical fitness of the person. Okay. And you can express in this form where your physical fitness is determined by these measurements that you can make. And let's say you measured the data from 100 or thousands of subjects. Okay, so this J essentially stands for subject number. So you've made a bunch of measurements where you want to relate the physical fitness of subject 1 as a linear function of the person's age, weight, height, and let's say body mass index. Okay, multiplied by the corresponding coefficients beta 1, beta 2, beta 3, beta 4, and beta 9. Okay, and let's say you've made this measurement for thousands of subjects, right? So you will have the same thing. Let's say you collect the data from 1,000 subjects. Now the question is, we have all these. We have the XI measurements. We have the YI measurements. Our goal is to identify these betas. Okay, that will give us the best fit between what is observed and what we are modeling using the linear equation. Okay, and that you can formulate as again an optimization problem like this. Okay, X beta is what you can predict from age, height, weight, body mass index. Y is what is the actual value, and the beta that we want to identify should be such that our predictions are as close as possible to Y. Okay, and if you formulate a problem like this, it turns out the solution takes a nice analytic form like this. Again, we'll look at exactly what that means in a few lectures. In a few weeks, you should be able to say exactly what that means. Okay. This is one way of looking at the problem. And the betas here simply tell you, for example, if xi is my age, right? Beta 1 tells me how age is related to my physical fitness. Okay. Now, here we only have five variables we are measuring. But imagine a problem where you are measuring a large number of variables, up to x 100 different variables, and you're trying to predict some another quantity of interest. And of course, you can, once you express it like this, and you have a fairly decent computer, you can solve the problem very quickly. You might be able to predict very well, but often the goal of models like this is not just to be able to predict somebody's, not just to predict the variable y, but also to gain some understanding of how these different variables actually predict y, and what are the most important variables here that actually predict y. Okay, so that is an aspect of, in stats where you are interested in not just how well can I predict, can I also understand what are the variables that are the most important in this model. That would, so indirectly what that would mean is, in an expression like this, the terms with the largest betas, okay, would mean that they have the largest contribution in determining the value of y. Okay, so in a way, large beta means that variable is important. Small beta would mean that variable is probably not that important. Okay, Now the question is, if you have a problem where you have 100 variables, how do we make sense of the betas? Okay. See, one way is to look at what betas are big and what betas are small. Another way to do this is, okay, we tell the program, okay, I want you to solve this problem, okay, but I don't just want you to minimize the error between prediction and the model, but I also want you to keep these betas to be keep the betas as small as possible. It turns out, when you formulate a problem like this, you can still get a nice analytical expression for solving this. What this will do is, it will essentially make the betas that don't have a lot of contribution to your output very small. Okay, so this is one way of identifying what are the factors that are most important, and even that's called the ridge regression. And the even more useful way of doing this is something like this. Again, what the two vertical lines mean and what the subscript means, all those things we will cover in the first 7 weeks. So by the end of 7 weeks, you should be able to at least look at something like this and say exactly what that means. Okay, and it turns out that something like this is actually quite useful. And when you formulate it like this, the solution that you get does not make some of the betas small, the betas that don't contribute so much. In fact, it makes it exactly 0. Okay, that's why this approach is is kind of is very nice. But unfortunately, it does not have an analytical solution like this. You have to use a computer to solve something like this. Okay. So this is again something we'll look at later on. And then finally, so stats is very, so machine learning is nothing but applied statistics. And maybe, but the difference is you're a little bit less rigorous when it comes to machine learning. But when you're doing stats, you're pretty careful about how you're dealing with things. And the magnitude of problems you're dealing with in machine learning is also much more complex than what you'd come across in traditional statistics. And so you are dealing with much more complex models. The data is usually again high dimensional with complex structure, and linear regression still forms a core part of modern day machine learning, right? And there are lots of other things: decision trees, support vector machines, neural networks, and these are all again models with a lot more complexity than what a linear regression model can offer. Again, we will not cover any of these as part of the one short lecture that we have on machine learning. We will only focus on linear regression and logistic regression. But once you are comfortable with the material that's covered, then many of these things again should be easy for you to go and study by yourself. Okay. All right, so that's hopefully that gives you the broad range of areas where this is going to be, these topics are useful. And my hope is that this course will at least prepare you to be able to comfortably work with similar problems that you might have in your own field. Okay, so that's that's the end of the broad overview that I wanted to give. So if there are any questions so far, we can talk about them before we move on to the actual core material of the course. Are there any questions? No? Okay. See, the first 2 lectures and maybe the third one as well is very dry, and it's full of definitions. But okay, the good thing is you don't have to understand them. Okay, you only have to remember them. Okay, and if you remember and you simply do it a few times, it will start to make sense. Okay, you'll get more comfortable with it. So don't be put off by the dry material. Just make sure that if there is something that is defined in the first 3 lectures, you absolutely remember it and you blindly apply the definition in situations where you have to find out something. Okay. Okay. The first topic we will start with is on vector spaces. And if something is not clear, just stop me there, and then I'm happy to explain things. Okay. Okay. So the first two lectures, as I said, talk about this concept of a vector space. And before we look at vector space, we'll talk about what vectors are. You're probably already familiar with this idea of vectors in physics. Okay, what are vectors in physics? Right, these are quantities that have both direction and do you remember how you expressed a vector in physics? Okay, okay. Geometrically, yes. Okay, it was represented like this. But how did you write it mathematically? So you wrote something like this, and then you write ax I cap, ay j cap, az. Yes, you remember this? What are ax, ay, az? Do you remember? What were those? These were called the components of the vector along the three directions x, y, and z. Okay, all right. It turns out the vectors that we are talking about here is essentially the same, except you don't express it like this. We express for us to talk about A, the only three numbers that we need are x, a, y, z. So we don't add these additional decorations A, I, j, and k cap. We simply use the three numbers ax, ay, az, and this is at least in mathematics, this is a representation of a vector. Okay, but again, one theme in mathematics is in maths, mathematicians are always interested in abstracting things and expressing them in the most general form. So of course they don't stop with 3. They say it can be any number. Okay, so it can be n numbers if you want. Okay, so in maths you might, at least here, for now, a vector is essentially a list of numbers. Okay, and for now we'll only focus on a finite number of numbers. Okay, you can have infinitely long vectors as well, but we won't deal with them. So a set of numbers is a vector, but again, importantly, it's an ordered list. That means the order in which you write the numbers matter. Okay, so in this particular case, 1.2 comes first, minus 0.1 comes second, so on and so forth, and then the last number is minus 1.24. Okay, whenever you have an ordered list of numbers like this, then that's a vector. And the convention I'll follow in the lecture slides, again, we'll make these available online, and we'll send you the link so that you can download the slides. The bold phase small letters would represent vectors for us. In the lecture slides, if you see something bold, small case, bold letter, that's a vector. Okay. And what is inside these vectors, the numbers here, those are scalars. Okay. And for us, these scalars can be anything, it can be a real number. So again, for people that are not familiar, how many of you are familiar with this expression? What do these mean? R, C, everybody is familiar? Right, this is the set of real numbers. This is, okay, all right. Right. So the individual numbers that you have in a vector come from one of these fields. Okay, and when we are talking about manipulating numbers within a vector, the same rules that are applicable for real numbers and complex numbers will apply here. Okay, so there are no new special rules that are proposed here. So the same rules apply. And in this course, the scalars that we will deal with will essentially be real numbers or complex numbers. In case you are not familiar with complex arithmetic, we will have a short intro later on when we will deal with complex numbers. But for now, the first few lectures, we will only deal with real numbers, right? So we don't need anything new for that. Right, now, a vector, when I write on the board, I might use an underscore to represent that it's a vector. Okay, this is a vector V, right? And the individual scalars, the convention I'll follow is I'll write with a subscript. Okay, so the first element is V1, second element is V2, so on and so forth, Vm. Okay. Again, notice that these are not bold faced. That means it's a scalar. Okay, and I simply means it's the ith element in that order. So this is V2, Vn, and so on and so forth. Okay, and when you have a vector, you could ask what is the size of this vector, or in the future if you see me ask you what is the size of this vector B, it's nothing but the number of elements you have in that ordered list. Okay, so in this case it's n. Okay, a force vector in the real world would have, what would be its size? Let's say I'm applying a force. What would be the size of that vector? 2, 3, generally 3, no? Because I can apply in any direction, x, y, z. So it will be 3. Yeah. Right, now, okay, let's say these numbers come from our real numbers. Okay. So in that case, what we would say is this is a vector with n real numbers. So the set that this vector comes from would often be written like this. Okay, which is this. So we know that this is the set of real numbers. Okay, if I write it like this is essentially a set of n real numbers. Okay, where the order matters. Okay, so that's what that means. If each of these was a complex number, then you'd say this vector is an element from Cn. Okay, what about force in the real world? Where is that from? What set is that from? There are 3 real numbers, so it should be from R3. Is that clear? Okay. Right. Now, let's say we have 2 vectors. Okay. Sorry, I'm all over the place. I'll try to be a little bit more organized. Let's say we have 2 vectors, V1 and V2. Let's say both of them are from Rn. Okay. We can talk about 2 vectors being equal if they satisfy 2 properties. Okay. Both of them should have the same size. That means they have to be from the same space, Rn or Cn or Zn or whatever. And each element of the first vector must be equal to the corresponding vector in the second element. Maybe I should not use V, I'll use A and B. That means AI should be equal to BI for all i's. That means A1 should be equal to B1, A2 equal to B2, and so on and so forth. If both these conditions are satisfied, then you say that the vector A is equal to vector B. Otherwise, you say they are not equal. Okay. Okay. That's again another definition you should remember. And there are some special vectors that we will come across that we will often talk about. So they have special names. The first one is called a unit vector, and it's usually written like this. At least in this course, we will follow this convention, bold E. And here I've written E1, and this is nothing but a vector of zeros except in one location. Okay, and that one location where it's non-zero, it assumes a value of 1, and that specific location is given by this subscript. Okay, so E1 would mean it's 0 everywhere. We will assume that this is from Rn. That means it's a vector with n elements. Okay, because it is E1, the element in position 1 is non-zero, and that's exactly 1. What would be E3? Yeah, so it will be 0, 0. In the third position, it's 1. 0. Okay. So, and these are called unit vectors. Okay. That means, okay, question for you. If you're talking about vectors from Rn, right? How many unit vectors can we have? N unit vectors, right? 1 in each of these locations, right? There can be n unit vectors. And it turns out that actually has that these vectors actually have an important role to play in all this. That's why it has a special name. And then 0 vector is all of 0. So it's, at least in the lecture notes, you will see, if you see a bold 0, that means it's a vector of all zeros. If it's 1, it's a vector of all ones. Right? And as we discussed before, these vectors have a geometric interpretation. Okay, at least in when we started, you said the vectors that we deal with in physics have a direction and have a magnitude. Okay, and the vectors that we dealt with in, at least in high school physics, were always 3-dimensional. Right? But in maths, we don't have that restriction. Okay, we can conjure up as many dimensions as we want, and it turns out that same geometric picture can be applied to the higher dimension as well. So, for example, if I have a vector v that is from Rn, okay, again, if you're not familiar, if you see something like this that looks like an E or epsilon, it means v belongs to Rn. Okay, all right. If you take a vector v from Rn, you can again. That means V is simply a bunch of n numbers. You can at least say you can see it. You can think of this as a vector, means an arrow pointing in some direction and with some length, sitting in this imaginary space or space that we cannot really visualize, Rn. Okay. In 3D we can see it. We can see it in our head. But in higher dimensions, you simply imagine that there is this space that exists that we cannot visualize, and any vector v is simply a pointed arrow in that in that space. Okay. So that would be the geometric interpretation of a vector. Okay, as an arrow pointing in a direction and with a certain length. And there are two operations that are often useful when dealing with vectors. Okay, the first one is vector scaling, which is simply you take a vector, okay, again belonging to Rn. Scaling is simply an operation of taking the vector and multiplying it by some scalar alpha. Okay, okay, and what that means is V was originally V1, V2, Vn. Okay. When you say you're scaling a vector by alpha, you simply take alpha and multiply it to all of the individual elements of your vector. So this means the scaled vector alpha V will be alpha times V1, alpha times Vn. Okay. For example, let's say A is a vector 2, 4. And what space is this from? What space is this vector from? R2, no? Okay. What would be minus 3 times A? If I scale A by minus 3, what would be the corresponding vector? Right. As simple as that. Okay, that's scaling. Now, we just slightly before I said there is a geometry associated with, or a geometric entity associated with the vector. What might be the geometric operation associated with the scaling operation? The algebraic. So this is the algebraic scaling operation. What might be the corresponding geometric operation associated with this? When you say you're scaling a vector, right? So algebraically, when you say you're scaling a vector by a number alpha, that means you're multiplying each of the individual elements of that vector by the number alpha. I'm asking what might be the corresponding geometric operation that you're doing. Let's say this is a vector A, and if you multiply it by alpha, what might alpha V look like? Addition, is it? Addition of what? See. Okay. 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 Even though we cannot visualize in Rn, we can visualize in R2. Okay. So usually how you draw R2, right? A plane. Right? What would this vector look like? 2, 4 in R2. So 2 units in this direction, 4 units in this direction. Maybe I should not have taken 3, but that's okay. This would be 2, 4, which is right. Okay, let's not take 3. Okay, maybe I will take one more change. Let's say our vector is 1, 2. Otherwise, I'll run out of space. That's this vector. Yes, you agree? 1, 2 would be this vector in R2. Right? Now, if I were to multiply by 2, what would be the corresponding vector? What would that vector be here? So 2, 4 that's here, that's this vector. What have we really done? Yeah, you've taken this and then you've stretched it along its own direction. You've not changed the direction, you've stretched it. Okay. What would happen if I did this? Right, you're doing the same, but you're stretching it in the opposite direction. So that would be this. What would happen if I do this? Yeah, you're squishing it to 0. Okay, so that's the corresponding geometric operation associated with scaling. Okay. Scaling, right? And another useful operation is this operation of addition. Addition of two vectors. Okay. Before we move on, I should also point out some of the properties that that scalar multiplication satisfies. Again, standard, commutative, associative, and distributive. Okay. These are again things you remember, which is again straightforward. Okay. There is an addition operation you can define on. This involves two vectors. Let's say we have two vectors V and W from Rn. Okay, which means these are two vectors with n elements. That's what the statement means. Okay, so V would be V1, V2, Vn. W is W1, W2, Wn. An addition operation between two vectors simply means this. You take the corresponding elements and simply add them together. So V plus W would simply mean would be a vector that looks like this. 1, 2. Okay. Again, algebraically very simple. Okay. This also means that you can only add vectors from the same space. You cannot add R3 to R, something from R3 to something from R2. Yeah. Okay. Now, what might be the geometric interpretation of this operation? Scaling is clear. You're simply taking, if you scale by a positive number, you're stretching it. Oh no. If you're taking a positive number greater than 1, you're stretching it. If it's a positive number less than 1, you're squishing it. Okay. But if it's negative, you're also reversing the direction. What might this be? Okay. Maybe we do example in R2, right? Let's say we have A, which is 1, 2. Okay. What will these two vectors look like in R2? A will look the same as that, 1, 1. That's A. What about B? Well, 1, 2, right? Sorry, yes, that's wrong. Right. Okay. What about B? Where will here? Right? Where will A plus B reside here? What will be A plus B? Where would that be? Here, right? So this would be. What's really happened? No, sorry, we've not talked about vector space. No, we are only talking about vectors. Right, exactly. That's what we're doing. So the addition of there, if you think of scaling as a box that does, let's say you have a box that does the scaling operation, it takes one vector as an input and spits out another vector as the output. So if you put in V, you'll get alpha V. Assume that box only does scaling by alpha. Okay, input is one vector, output is one vector. Whereas this addition operation is slightly more complicated. It takes two inputs and then spits out one vector. Okay. But what has happened here? Can we make sense of what is going on here geometrically? Okay, How many of you remember this? The parallelogram law of addition? Addition of vectors? Do you remember? What is that? No. What is a parallelogram? Right. Is this a parallelogram? At least a crappy version of a parallelogram? No, length and width cannot be parallel, right? Because then they'll be along the same line. No? The two opposite sides are parallel to each other, right? Right. So, if you don't remember the parallelogram law of addition, this is what you do. So you have A and B, okay? You form a parallelogram using A and B, okay? And the way you do that, this is A, this is B. You simply, from the end of A, you draw a line along the direction of B that is parallel to B, okay? That's here. And then from the end of B, you draw another parallel line along the parallel line to A, and then it will turn out that both of them will meet at a point. They will meet at a point. There are two non-collinear lines, or I mean, there are two lines that are not parallel to each other. That means they will meet. They will meet at a point. Okay. Now, if you draw a vector here, which is essentially the diagonal of the parallelogram. This is here. Yeah. So that's what is happening here. So when you do the algebraic operation of adding two vectors, what you're doing geometrically is you're doing the parallelogram. You're applying the parallelogram law of addition of vectors. Okay. So one way to think about this is, let's say these vectors represent somebody's movement in R2. Okay. When somebody says that I initially moved by A and then by B, that means they'll eventually end up here. It means if I move by A and then move by B, then I get here, or the other way around as well. This is commutative. If you first move along B and then move in the direction of A, then you end up at the same place. Okay, so that's one way to think about this. Is the net effect of moving along these individual directions in whatever order. Okay, I hope that's clear. Okay. So again, there are some basic properties. It's commutative. That means you can switch the order, and the result is still the same. It's associative, so that means if you add three things, the order in which you add them together, it does not matter. And if you add any vector to the zero vector is simply a vector of all zeros. So if this was the zero vector, again it's clear why that is the case. And you can also do what is called a subtraction of two vectors, but that involves the the scaling operation as well. For example, if you take A and then if you take minus 1 into A and you add them together, you'll always get the zero vector. Okay. So which essentially means if I move along A and then I move back in the opposite direction of A, I will essentially come back to where I started from. Okay, right. Okay, before we move on, you could ask, okay, maybe you're thinking, okay, these two make sense. Maybe you're thinking, what about the third operation? You talked about addition, you talked about scaling. Maybe another interesting operation is vector multiplication. No? And you can define it as multiply the individual elements. I need to write it properly. Right? That seems like a legitimate operation, right? Maybe you're thinking, maybe there should be something like this. It turns out, well, of course, you can define an operation like this, but this is not something that people study, because it turns out this is not that interesting, at least mathematically. So we don't have something like this. We have something else, which we will come to later. So often, and the point I'm trying to make with this is, with many of these things, with maths like this, the definitions of many things, what is defined, what is not defined, might seem arbitrary and might seem very confusing. But remember that these are not ideas that have originated just like that. These are ideas that have been around for a very long time. Many people have thought about these things and have struggled with these ideas and have finally boiled it down to a point where the things that I am telling you here are the core things that we need to know to be able to work with these things. That's the reason why I'm only talking about these things. And if you take any linear algebra book, they will again only talk about these things, because turns out lots of other things are not really that useful or interesting. I'm sure somebody looked into this and then they found, okay, it's really not, it does not lead you anywhere mathematically, so they said, okay, this is not something that we need to look at. Okay, so that's why we only talk about these two, and these two are again important because that then leads us to this idea of a vector space. We only have 5 minutes. I will just introduce the idea and then we'll take it up from next class. Okay. So before we talk about vector spaces, right? How many of you are familiar with the concept of a set? Yes. What is a set? Yeah. Again, fairly simple. It's simply a collection of stuff. Okay. You could ask what stuff. That's up to you. Okay. You define what goes into your set. And your definition needs to be clear in such a way that if I were to find out whether something belongs to your set or not, I should be able to do that without any ambiguity. Right? For example, I could say set of real numbers. Okay? I can give you a bunch of numbers. Because I've defined what the set is, you can, if I give you a number, you can tell me whether or not that number belongs to that set. Right? So that's essentially the idea of a set, right? Collection, but the membership definition has to be very clear. Okay, and that leads us to this idea of a vector space. Okay, again, the most important thing to remember: a vector space is a set. Okay, so tomorrow when I ask you what is a vector space, the immediate thing that should come to your mind is that it's simply a collection of stuff. Okay, and what is it a collection of? It is a set of vectors. Okay, it's simply a collection of vectors. Okay, but that's not enough. Okay, if you have a collection of vectors, okay, that's fine. But it turns out that there are two conditions that this set needs to satisfy before you can call it something special, a vector space. If you simply have a set of vectors, it's simply a set of vectors. It does not form a vector space. But if it satisfies two additional properties, then it becomes a vector space. Okay, and those two properties are related to this idea called closure. Okay, again, all of this might seem weird. Just remember it. Okay, or this idea of closedness. Okay, the first condition is if you take a vector. Let's say if you take a vector V. Let's say the vector space that we are dealing with. Let me represent it by capital V. Okay, V is a vector space if I take a vector that belongs to V, okay, and I simply scale it by some arbitrary scalar, it has to belong to V. Okay, that means if I take the vector, I scale it, that vector should already be present in my original set. Okay, this has to be satisfied. That's one. The second one is it should be closed under vector addition. That means if I take two vectors, okay, then then V1 plus V2 also belongs to V. Okay, if these two are satisfied by a set V of vectors, then it is a vector space. Okay. Okay. What does this mean geometrically? Okay. Let's say this is my space. Okay. This is the space I have. This is that space I'm interested in. This is that space V. Right. Now, if I take a vector V and I stretch it, compress it, reverse the direction, stretch it, compress it. No matter how much I stretch or compress or reverse the direction, that vector will always remain within the boundary of this set. Okay, that's the first jump. That's what the first condition means. The next condition is if I take V, another vector, and if I add them together, if I apply the parallelogram law of vectors, the new vector also remains within this boundary. Okay, which also means that this is a definition, and then you have a set of consequences because of these definitions, and some of them are listed here. Again, the first two properties are standard vector addition properties, commutativity and associativity. A third property, again, that can be derived from here, but still something useful to remember, is there has to be a zero element. Okay, which I'll simply write like this. Okay, a zero vector. Okay, that means in this vector space there has to be a zero vector. That means if I add that vector to any vector that I have from the vector space, you get the same vector. Okay, so you need to have the zero vector. I mean, that is probably obvious, because now if you scale, the first property is satisfied, right? That means no matter how much I scale or compress the vector, you're still within that set. If I simply choose alpha to be 0 and V is a vector space, that means 0 has to be in the vector space. Okay, then again, but I still add it as another property or constraint or property, because it's better just remember this, that if you say something is a vector space, it has to have the 0. If it does not have the 0, it's not a vector space. Okay. Yeah, and that's it. That's the definition of what a vector space is. Okay. It's already time, so I will stop here, and then we will send you an email later today with these, so that you can download these slides, and then we'll take it up from next class. Are there any questions so far? Okay, all right, thank you.